introduce Jordan Dahl. She's a student at Ben Labs research group, and she's going to present her thesis work, and she plans to defend coming up in the next month or so. So stay tuned for an announcement about her defense when it comes when she's ready to do that. So, all right, Jordan, I'll turn it over to you. Welcome, everybody.
Great, thank you. Get this shared. Can you see my screen?
Looks great.
All right. So thank you for the introduction.
Good idea.
I know I haven't had a ton of time to get to know everybody my time here at NDSU. Happy that I get to share some of the work that I've done. So the title of this presentation is Snow, Ice, and Climate Change in Great Basin National Park. But today we're going to talk a bit more about the Great Basin region as a whole. I'd like to give my acknowledgements first. I want to say thank you to my advisor and my amazing committee members, as well as our research group. I couldn't have done any of this stuff without them. And then the National Park Service for permitting everything, and our funding agency, and the Prime Lab at Purdue. So let's orient ourselves a bit. So we're working in the Great Basin region of the Western US, which is outlined in black here. This is not a map of the modern Great Basin. As you can probably tell, there aren't giant lakes in the middle of the desert, not anymore. And this is a region located in, at least part, the Basin and Range geologic region. And this is an area of extensional faulting. So all of these north-south trending ranges formed through extensional horst and graben faulting. And this is an extremely arid region, but the landscape looked a bit different 20,000 years ago when we would have had an ice sheet covering us. So we're talking a little bit about how different the environment was and how it changed over the deglaciation. So pictured here on the left, we can see several alpine ranges that we'll discuss in a bit, but these, besides the ones that are pointed out, all of these ones with white caps were glaciated at some point during the LGM. Those that are highlighted are just the ones that we're going to talk about for regional context. Specifically, though, we're presenting results from the South Snake Range along the Utah-Nevada border. This is a desert rain shadow environment, and all of these ranges have evidence of past glaciation, and then these large valley lakes are evidence of the pluvial environment that supported these glaciers and lakes. So the South Snake Range is home to Great Basin National Park, which I've talked about before in my proposal talk. I talked a little bit about the dating that we've done, and then also the Wheeler Peak Rock Glacier. But we're going to go into a little bit more depth on the dating, and then the more in-depth discussion of the Wheeler Peak Rock Glacier is going to be saved for my defense talk that's coming up. So if you want to hear about that, you can join us later. So there are two moraines in the Great Basin National Park that we are going to be talking about. The LGM terminal moraines of Baker Creek Valley and the recessional moraines, which represent an approximately 50% reduction in glacier length. And then just for context, that's where the Rock Glacier resides. The other notable features of Great Basin National Park are, there are several other notable features, but there are a number of other rock glaciers, and then Lehman Caves is a cave system which has been studied for its Speleothem paleoclimate record. And then what are these moraine things that we keep talking about? Alpine moraines can form through a number of processes. These are shown here on the right. They can form through ice advance plowing up debris and creating a push moraine, through deposition of superglacial debris through slumping or some process such as that, or the ablation or melting at the toe of the glacier. We don't really care about how they form, but what they mean. So they represent a pause in glacier advance or recession. Just means the glacier sat there for a long enough period of time to leave a moraine deposit. And then as a glacier recedes up valley, if there are any pauses in recession, it may deposit a recessional moraine. And these can create sequences of moraines up valley from oldest at the bottom to youngest at the top, because if the glacier readvances, it will likely destroy any previously constructed moraines. So you always end up going from oldest to youngest, and when we can date these, we can create a chronology of glacial recession. So that's the goal. And how we date them is through glacial erratics. So moraines are composed of glacial debris of all sizes. We know this because a lot of the soil in our environment around us is, here in the Midwest, is glacial till. There are often large boulders in inconvenient places that farmers have to avoid. And these boulders are considered glacial erratics. We're looking at ones that are specifically emplaced at the crests of glacial moraines because they represent that period of time when the glacier sat long enough to deposit that moraine. And then pluvial lakes. So you may be familiar with Lakes Lahoshan and Bonneville. They're very prominent features of the late Pleistocene Western US, but you probably haven't heard of Lakes Franklin and Clover. They're these much smaller pluvial lakes in northeastern Nevada. All of these have been created because of an environment with enhanced effective moisture. So that just means by whatever mechanism, there's just more moisture in the environment, either increased precipitation or decreased evaporation or a combination of both. These generally form in closed basins. The two that we are discussing in specifically are both closed basins, and these can be similar chronologies to the glacial moraines can be constructed through the dating of shoreline ridges. So these are created through back and forth wave motion, and they can be dated through optically stimulated luminescence or through radiocarbon commonly. And these methods allow us to create similar chronologies to the glacial moraine chronologies, expanding our base of understanding about climate in the Great Basin. So let's get down to the nitty gritty. What are our research questions? We really want to know how the climate changed through the last deglaciation. And generally, we're going to try and get into that by looking at the Baker Creek Valley Glacier. That allows us to gain another piece of the puzzle of glacial retreat at the end of the Pleistocene. And we also want to understand what the pluvial lake chronologies, in conjunction with some previously done glacial modeling, can tell us about temperature and precipitation conditions that could have supported both pluvial lakes and alpine glaciers. So getting into a bit about cosmogenic nuclide exposure dating, we're going to talk a bit about the theory and how cosmogenic nuclides are produced. So beryllium-10 is a cosmogenic nuclide. This is produced by interactions between cosmic rays and oxygen atoms. The reaction occurs between these cosmic rays and particles in our atmosphere or at the Earth's surface. And the specific interaction that we're looking at is called a spallation reaction, where the atom is interacting with, or the particle is interacting with an atom, impacting and it's separating that atom into subatomic particles and the cosmogenic nuclide that we're targeting, which is beryllium-10. Specifically, we're interested in the reaction that occurs between cosmic rays and oxygen atoms in quartz grains. So we're looking at quartz-rich boulders that are deposited on moraines, and within these quartz grains, the oxygen atoms are going to be bombarded with cosmic radiation, and at a certain production rate will produce beryllium-10. So when a number of samples from a moraine are dated, we can average those ages in order to give us a good approximation of the age of that glacial moraine. So production rate, I mentioned, is controlled by a number of factors. Two very important ones are geomagnetic latitude and elevation, or depth in the atmosphere. The largest influencer is depth in the atmosphere, or elevation. For every meter of decrease in elevation, you get a factor of 2 decrease in production rate. And then the geomagnetic latitude is also a strong factor, but is not quite as does not quite have as much of an impact on the production rate. Down here on the right corner, we can see different regions, and they're different regions that are used for calibration. So you can calibrate your ages either globally or with a local set of data. And what we use is Promontory Point right here. This is in Utah. So we can use a smaller set of local data in order to get a more regionally applicable age. So when we sample, we need to take all these things into consideration, including sample thickness and density, because the production rate of beryllium-10 decreases rapidly as you go further into the surface material. You need to consider what's called shielding, or anything that would impede the interaction between cosmic rays and the surface. So it can be topographically shielded by a valley wall, or if it's not at the crest of the moraine, it could be topographically shielded by the moraine. It could shield itself if it does not have an even shape to it. So we're looking for boulders that have a relatively flat surface at the top that won't have any self-shielding, and any topographic shielding needs to be recorded appropriately. And then we need to make sure that there isn't significant surface erosion on the boulder that would give us pause and make us worried about whether or not it would give us an accurate age. If large amounts of material have been removed through erosion, then we're not comfortable sampling it. So when we bring all this stuff back to the NDSU Cosmo Lab, we go through a number of steps to prepare it for beryllium-10 extraction. First, we need to separate it out until it's the target grain size and isolate quartz grains. And then when we have quartz grains isolated, we go through an acid etching process where we remove any remaining grains that aren't quartz, and we remove any meteoric beryllium-10, because beryllium-10 can also form through interactions with oxygen in the atmosphere. And we separate any final grains that aren't quartz. Go through a dissolution test to see if it's ready, and if it passes, we're good to go into beryllium-10 extraction, and if not, then we head right back into etching for another round or two. And then beryllium-10 extraction is a kind of complicated set of chemical processes where we do a dissolution, conversions, ion separations. I'm happy to talk about that at some other point, but I'll just leave it at this, that we Our final product is beryllium hydroxide, and we pack that into a cathode with a binder and send that off to the prime lab at Purdue. And they return to us our results in the form of beryllium 9, beryllium 10 ratios. So we convert these ratios into a ratio which is equal to the number of beryllium 10 atoms per gram of quartz in our sample. And then this number of beryllium 10 atoms ratio is used in conjunction with our sample site parameters to calculate exposure ages for each individual boulder. When we look at all of these boulders, we analyze the distribution to make sure that we don't have any sort of like systematic error or any outliers that are going to skew our average. And then after deciding that, we will report our final average. So our final averages for the lateral moraines at the LGM extent of the Baker Creek Valley Glacier are 21,000 years plus or minus 0.6. And the recessional moraine at about 50% of the total length is 14.0 plus or minus 1,000 years. Over here on the right, we show the individual sample ages for the lateral moraines, and you can see they're really well grouped around 20 to 21,000 years, but there's one sample that is aged a bit younger than the others. So we want to show a bit about the distribution. So we plot these up, Spox and Whisker and violin plots, so that we can see how the distribution looks and if we have any outliers. And we're comfortable saying that this youngest terminal moraine age is an outlier, as it does not overlap within uncertainty with any of the other terminal moraine samples. And you can see when we remove it from the pool, the distribution becomes a lot more uniform. And also we report the reduced chi-squared statistic down here in the lower left-hand corner of each of these. And removing that sample drastically improved the reduced chi-squared statistic. With reduced chi-squared, it's a measure of confidence that the variation that you see is due to measurement uncertainty alone. So a value around 1 would tell you that the uncertainty is due to measurement uncertainty alone, and a value distinctly different from that would give you pause and make you concerned about some systematic error. This reduced chi-squared from the recessional moraine is not too different from 1 to give us major pause, but we're much more comfortable with this value. The youngest sample from the recessional moraine just barely overlaps with an uncertainty with this next youngest sample, so we've decided to retain it in the data set. When we compare these averages to other moraines from those ranges that were highlighted in the map in the beginning, we see this. So the moraines in blue here are terminal moraines. The moraines in red are what we consider down valley recessionals, and that would be recessional moraines that are within 75% of the total LGM extent of the glacier. And then in green, we have up valley recessional moraines. Those are at less than 75% of the LGM extent. The recessional moraine at Baker Creek is around 50% of the maximum LGM extent. So these ranges are listed from west to east and north to south where necessary. And Labs et al. 2020 looked at all available cosmogenic nuclide exposure ages from the Western US and found that there's an average terminal moraine age of 19.5 thousand years and an average down valley recessional moraine age of 17,000 years for all of the Western US. So our terminal moraine falls well in line with previously studied terminal moraine ages. We don't have any down valley recessional moraines preserved in the Baker Creek Valley. They may not have formed, they may not have been preserved, but this up valley recessional moraine does overlap within uncertainty with the youngest moraine from the Santa Rosa and the Wasatch, just ever so slightly. It's a bit younger than what we would have expected. And actually, this youngest one up here is not a moraine age, it's actually a bedrock exposure. So that would mean that the glacier eroded down to bedrock, and as it receded, it exposed this fresh bedrock around 13.4 thousand years ago. So based on this regional context, what can we say about our ages? We can say that the terminal moraine is, it agrees really well with other LGM terminal moraines, and it doesn't give us any pause. The recessional moraine, it agrees well enough with the Wasatch and Santa Rosa, but it aligns really well with this Overland Creek Valley and in the Root Mountains. And it's interesting because the persistence of a glacier at this 50% length until 14,000 years ago suggests that at least in some of these high mountain ranges, glaciers could have persisted until the beginning of the Heinrich Stadial 1 warming interval, and even until pluvial lakes began to fall. So let's talk about these pluvial lakes a little bit. So now we're going to talk about a water balance model for pluvial lakes in the Great Basin. So again, as all of pluvial lakes, these are specifically located to the east of the Ruby and East Humboldt Mountains. Lake Franklin to the south was dated by Monroe and Labs in 2013, and Lake Clover to the north was dated by Monroe in 2020. We'll look at them individually and all of the specific shorelines that were dated in a second, but I want to talk about the model and how it works a little bit. So this is a water balance model that was originally developed by Condom et al. In 2004, specifically for closed basins. So basins that don't have any natural outlets. It uses modern watershed and climate data to determine a soil water capacity, or kappa S, for the watershed. And it was originally developed for use in the Andes of South America, but it has been adapted for use in the Great Basin by Doug Steen, I believe, and then Caitlin Fleming, who some of you may have been familiar with, presented on some work with this model a few years ago, and it's since been updated, and it specifically uses these modern watershed and climate data to develop the kappa S, soil water capacity, for the basin, and then you put the kappa S back into the model as a parameter in order to determine climate characteristics of the pluvial lakes. And we use modern here in quotes because modern watersheds are frequently diverted and modified for agricultural use. So we have to use historical watershed or historical lake levels and modern climate data. So because of this, we want to have a variation of modern lake levels in order to give us a range of kappa S values, which could support, which can be modeled, and will then give us a range of climate data, because it will be easier to make more broad statements, more broad predictions. We also need to address that this is and it is assumed that the modern Kappa S is a reasonable approximation for Kappa S in the Paleo Lake watershed. We justify this by the fact that there is minimal change to vegetation and geology and topography within the basins, but it's worth noting that that is an assumption that we're making. And then data is fit to these coded rasters. The blue denotes the watershed, the red, the Paleo Lake, and the yellow, the modern lake. This is specifically a coded grid of Lake Clover, and the modern portion of the lake extent is only used for the initial modeling to determine the Kappa S. During that modeling, the Paleo Lake would just be considered part of the watershed area. And during the Paleo Lake modeling, the modern lake extent will be considered part of the Paleo Lake. So then we can talk specifically about each of these lakes. Lake Clover was dated by Monroe et al. In 2020, with 6 shoreline ridges dated, ranging in elevation from 1,725 meters to 1,712 meters, and ranging in age from 15.9 to 9.5 thousand years old. Now, the oldest shoreline elevation at 1,725 meters was previously dated in another study at 19 and 17 and a half thousand years, so those will also be used in modeling. But the first 3 shorelines, 1725, 1720, and 1717 meters, were all constructed over a period of about 1,000 years, between 16 and 15,000 years ago. The next 2 shorelines, 1715 and 1713 meters, were built about 3,000 years later, between 12 and 11,500 years ago. We don't know what happened in between during that 3,000 year interval. There is no real way to know, because these shorelines could have been destroyed by the lake, or it could have not stayed in one position long enough to construct a shoreline. Just can't tell. The final shoreline at 1712 meters was constructed 9,500 years ago, and the modern lake is drawn here for you. At the time that this satellite imagery was taken, the lake was dry. It's an ephemeral lake called Snowwater Lake. And to give you a little context, that's the modern extent. And then Lake Franklin to the south. This one was dated by Monroe and Lobbs in 2013. There are 3 shoreline ridges, 1850, 1843, and 1830. So between 20 and 17.3 thousand years ago, there was a stable elevation of 1830 meters. So we were at a lower elevation until this abrupt expansion happened over a couple of centuries and increased the lake level to 1,850 meters. And then by 15,000 years ago, the lake had receded to 1,843 meters. So that was that middle one there. And the modern extent of this is pretty much non-existent. This is not a lake body. This is a permanent marshland that's fed by streams coming off of those mountains in the lower portion of the range. This is actually, I think, a national preserve, which is pretty cool. So we compare models built off of these shorelines using that water balance model by Condom et al. To glacial models, which have been constructed by past students of Dr. Lobbs for Overland Creek, Seats Canyon, and Angel Lake and these are all in the Ruby and East Humboldt Mountains. As you can see on this graph, the vertical axis value of 1 is equal to modern precipitation, and each other value is a factor by which modern precipitation would be multiplied. That goes for all of the graphs you'll see in the next few slides. So for Lake Clover, 3 of the shorelines we discussed overlap with contemporaneous glacial models from the Ruby and East Humboldt Mountains. So only 3 of them can be used in this comparison. Each of them is shown with their high and low kappa S value models respectively. The high kappa S is 7,100 millimeters and the low kappa S is 7,400 millimeters. And we can see that this value of 1 on the vertical axis is at the horizontal axis. So Lake Clover, for every temperature depression that we modeled, predicted a higher than modern precipitation required to support the lake. Lake Franklin is a little bit different. With the high kappa S value, it also predicted an increased precipitation required, but with the low kappa S value, it was not predicting an increased precipitation for everything. If you have a temperature depression more than 3 to 5 degrees C, then it actually predicts a lower than modern precipitation. The high and low kappa S for Lake Franklin are lower than the high and low kappa S for Lake Clover by a good degree. This indicates that there's less soil water storage capacity in Lake Franklin. So our first interval of comparison is 20 to 19,000 years ago. In this interval, we see that an overlap of Pluvial Lake and glacial models indicates that there was a between 10 and 12 degree temperature depression, and there was roughly modern precipitation. At the time interval 17 to 15,000 years ago, what we see is a broader prediction because there's just a lot more models being thrown together here. But it's an increase in temperature from previous. So we have between 7 to 10.5 degree temperature depression, and then potentially slightly elevated precipitation with the prediction ranging from 0.6 to 1.7. And what we see in the last interval that we look at is a temperature depression now from 5.5 to 7.5, so definitely an increase in temperature and definitely an increase in precipitation, with the prediction now being between 1.2 to 1.8 times modern precipitation. These are a little bit hard to visualize individually, so we plot them all together. And what we see is this progression from the LGM into the height of the Pluvial Lake high stands, and then the last interval actually containing the Dryas. But over this interval, we see a prediction of an increase by about 6 degrees over that 9,000 years, and an increase in precipitation by about 50% over those 9,000 years. And now we can't make any statements about exact paleoclimate conditions, but what we're showing here is that temperature and precipitation combinations from within these highlighted regions may have been able to support glacial and lake extents modeled during these time intervals. So what do we see when we compare this to previously published climate records? All of this work has been aiming at understanding what climate was like in the Great Basin at the end of the last glacial maximum. So there are a number of really well-documented proxy records available within the southwestern US, and a recent study from Laura and Ibarra has used all of these, a number of these proxy records in conjunction with this model called the transient climate evolution of the past 21,000 years. And this is compared in order to communicate how much we know about how climate changed in North America during the last deglaciation. So this model uses LGM conditions as initial state conditions and applies forcing mechanisms, including orbitally driven insulation change, atmospheric greenhouse gases, meltwater fluxes, land ice volume, and ice position. And they see that it has good agreement with proxy records from around not just the southwestern US, but around the US as a whole. And you can see here that the results are pretty focused on the US, not just North America, but we're going to focus even more closely on the southwestern US, which I've highlighted here in red. And these individual boxes pull out to show the trends in temperature over a 10,000 year interval between 20,000 and 10,000 years ago. We see in blue are winter temperatures, in green are spring temperatures, in yellow are fall temperatures, and in red are summer temperatures. There's no significant change in winter, spring, or fall temperatures, at least not much significant change. We definitely see an increase in summer temperatures throughout the interval. And we see this the same map, instead this time overlaid with precipitation. What's important to note here is the majority of the precipitation that's delivered to the southwestern US comes during the winter, the vast majority. And then this level of precipitation is maintained between 20,000 and around 15,000 years ago. Between 15 and 14,000 years ago, there's a drastic decrease in the level of precipitation being delivered. And then it kind of tapers off with a slight continuation of that decline. This is again mirrored in this plot that they provide, where they subtract evaporation from precipitation, which is a good estimation of what we were talking about before, effective moisture. So we see the same pattern with the pretty stable effective moisture between 20 and 15,000 years ago, and then this pretty steady decrease afterwards. What they note is that temperature didn't change much in the winter between 20 and 10,000 years ago, if you remember looking back at that other map, but precipitation definitely did. So this change in P minus E is primarily the result of precipitation changes and just a decrease in the amount of precipitation being delivered to the southwest during the winter months. We see a comparison now from the same study between this P minus E and Speleothem Records from Devil's Hole in Nevada. So what they find is that Speleothem Records are inversely related to the P minus E. This here in gray on the left is the Speleothem record from Devil's Hole, and this is the P minus E from the model. And this is consistent with what other studies have found, that Speleothem records are related to temperature, and you see lower Speleothem records at lower temperatures, and this would also be related to precipitation, as lower delta O18 values are related to the precipitation that is delivered from high polar regions, which is what is delivered during the winter. Lochniet et al. Found something similar in his 2014 study when he compared the Speleothem record from Leviathan Cave to the lake levels of Lake Lahoshan. So this, again, is Lake Lahoshan would be responding to effective moisture, which would be inversely related to the Speleothem delta O18 record. So to wrap everything up, shoreline ages from Paleo Lakes, Franklin, and Clover align really well with observations made by previous studies. These cold temperatures and high effective moisture supported the expansion of glaciers and lakes during the LGM. And then after that, warming and sustained high effective moisture allowed pluvial lakes to expand while glaciers receded. And then finally, we saw the continued warming that decreased precipitation and led to lower effective moisture and decreases in paleo lake extents. And the ablation of any remaining glaciers, including what we saw with the recession of the Baker Creek Valley Glacier. I would be happy to answer any questions. Thank you all for listening. Here are my references.
Thank you, Jordan. I'm seeing some people clapping. Is that maybe someone's raising their hand? Jim, do you have your hand up?
No, I was just clapping.
Okay.
Excellent presentation
Thank you.
and study.
Yeah, very nice, Jordan. So I'll pop in here while folks formulate their ideas. These recessional moraines and even earlier terminal moraines, so when a glacier readvances, it just completely eradicates what was there, or is there ever a case where the deposits are deep enough that you might still see them?
Well, glaciers are really powerful erosive forces, so it would be very rare to find a situation where a glacier would advance over a moraine and it would still remain intact. But it would likely, if it remained, at least have a lot of evidence that the glacier had done some damage to it, if that makes sense.
Yeah. Well, I'm just wondering how, when we go back in time, there's these estimates on glacial advances and retreats, and so the technique you're using works for the most recent one, right? But yeah, we have records, right? Or there's in the literature we see advances and retreats of glaciers at different points in time, and maybe this might almost seem like a defense question. I apologize for that. But do you know how those have been made, and do you have doubts about those estimates?
Can you repeat that last part? I missed a little bit of it.
So let's say there's an earlier glacial period, but the record of it would have been obliterated by the more recent one.
Okay.
How do you estimate the age and the behavior of the earlier one?
Right, so you wouldn't be able to get any specific moraine ages, but you can use other proxy records to understand glaciations in the past. So like Speleothem Records in caves give you a really good idea of what's happening globally when with the climate. And then you can use like benthic foraminifera to understand what's happening in the ocean. And these are all different ways that we can look globally, but specifically, I don't think you'd be able to understand like what a glacier in a specific valley was doing if the moraine was destroyed. There are a lot of places where there are moraines further down valley than the most recent terminal, and you could understand what was happening there. You could get the maybe maximum extent, but not recessionals.
Thank you, Jordan. Yeah. Nice job. Just go ahead and unmute yourself. If you have a question, I'll see if I can see if there's any hands raised. We'll be patient just for a little bit.
Yeah.
So just a little bit of a general question for those of us that aren't really as familiar with history over the past few thousand years. Could you go back to that change around 14,000 and discuss that a little bit?
From the model?
Yeah, from any of them, it shows up.
Yeah, it does show up in a lot. I'm gonna go back to the end. So this is related to, let me get this out a little bit.
the sharp one, right around 14,000.
Yeah, so this is attributed by these authors to changes in atmospheric circulation. So it would be a warming period that changed the position of the Laurentide ice margin, because the Laurentide ice sheet is thought to have deflected some storm tracks southward and delivered a lot of extra precipitation to the American Southwest.
Oh, okay. So that was fairly local. Wouldn't have been anything with Antarctic blocking flow or anything like that.
Yeah, there's a lot of discussion of that Antarctic meridional overturning circulation and how like globally it all interconnects. But this appears to be a more local event because if I go back here, this like stark decline isn't seen in the Pacific Northwest and isn't really seen in other places. It's just here in the Southwest. So that's at least what I gleaned from this specific study.
Okay, thank you.
Yeah.
So looking at this figure that you have up there, I think, when people have talked to me about glaciers, sometimes they use it as a proxy for slow. But retreats and advances can happen relatively rapidly, right? And I just wonder, would you like to comment on that? And also just thinking about how rapidly climate is changing right now. This idea that the global climates change at a gradual, that's probably just an really old-fashioned notion, I imagine, in your circles. People don't even think that way. Is that correct?
No, I get what you're saying, though. It's kind of interesting because I have only really studied like geology and then the more like environmental scale biology. So everything happens over really long time scales generally, at least in my area, like experience of study. But I mean, during my defense talk, I'll be talking about the Wheeler Peak Rock Glacier, which is the end member of a glacier, a potential end member of a glacier, where it's been so covered in debris and it's just insulated by this rock that only ice that is underneath this mantle of debris is insulated and left there. And it is living in the middle of Nevada in a very arid climate, but it is a really important feature, even though it's so small. It provides a lot of hydrologic resources for the town of Baker, as does the snowpack in that range, which not just the loss of glaciers, but the loss of snowpack is going to have a really incredible, not in a good way, impact on a lot of communities.
Yeah, and you may or may not be aware, but Las Vegas was planning to send a pipeline up to the kind of that area where Wheeler Peak is. I know they acquired water rights all the way up along that Nevada. And I don't know what's happening with that. I know that one of their more recent requests a little bit further south was denied by the water engineer because there's a lot of endangered species.
I hadn't heard that. I don't know if Dr. Lobbs had heard that, but no, unfortunately, we didn't get to go out to Great Basin again this summer, but I wonder if that is something that the people of Baker, Nevada have a lot to say about right now.
Well, it's interesting because they're historically out in Nevada, ranchers weren't very interested in having ichthyologists come on our land because they'd say, you're going to discover some endangered species and then I won't be able to do whatever I want, and then I'm going to have to kill that species before, and so just they wouldn't let you on. But now, if the water right of the endangered species might actually help them protect a spring that maybe they're not, maybe they use, but the usage would not be as critical as compared to, at least that's what some of the anecdotes I've heard.
That's really interesting. I mean, it's good that people are considering the fish species, even if it's a bit selfish.
I think so. Of course, that's my cottage industry. So